Shane Raviello, and I'm here to tell you about a project I've been working on for the past few months. For the project, we were given a situation where we had to take a 10 kilogram box and we had to move it from here to exactly here, rotating it 90 degrees in the process and avoiding hitting this corner in the movement of the object. What we had to do is we had to create a mechanism along with calculating the velocity, accelerations, and the forces found in the members of the mechanism as it moved. The mechanism we chose is a 6-bar mechanism. What a 6-bar mechanism is it is a 4-bar mechanism combined with a driver dyad that adds 2 bars to the mechanism. The entire mechanism had to be located on the base and cannot be outside of the base. First, in creating our 4-bar mechanism, to move the box from here to here, we had to choose an intermediate point. So we knew that we would miss this corner as the box moved. Once we had an intermediate point, we then created perpendicular bisectors to locate where our 4-bar mechanism would attach to the base and then to the box. You can see that here. You can see our 3 bars, 4-bar being the base. So this is the main 4-bar mechanism that will move the box from here to here. The driver dyad, located here, its role is to keep the box moving just from here to here, no more than that. It limits the motion of the box. You can see the 4-bar mechanism in the intermediate point. You can still see the 4-bar along with the driver dyad, making it a 6-bar. Along with the mechanism here, 4-bar dyad, fully extended out now, 180 degrees from the start point because it's at the end. So when this rotates back around, the box will move back to the top. You can just see some rough sketches here where when we were doing our position calculations, we were double checking with AutoCAD to make sure we had our angles right. Now we move on to analytically proving the position of the members. You can break a 6-bar mechanism down into 2 smaller 4-bar mechanisms, as seen here. The main 4-bar, along with the dyad that we can call a 4-bar, because we can take part of L2, which is part of the 4-bar, and call it L7, and that will be the 4th bar in the smaller 4-bar mechanism. With the 2 smaller 4-bar mechanisms, we added up our X and our Y components for each and set them all equal to 0. With these equations, we were able to put them into an Excel spreadsheet, and we were able to calculate the position of every bar as the driver dyad moves from angle 0 to 359, completing 1 revolution of the cycle. You can see over here our 4 equations from the previous slide. Now to solve these equations, to solve for the angles that would satisfy these equations as the bar moves, we had to use the solver function in Excel. Now what the solver function does is you can give it a set of constraints and you can ask it to change variables to find the solution you're looking for. So what we did was our objective is here, we set it to a value of 0. The constraints are the 4 equations previously shown, and we're changing the variables theta 2, theta 3, theta 4, and theta 5. And so what that does is we can take theta 6, we can set it to any number, and it will solve for what angle all the other bars are at, satisfying our equations, making them 0. You can see our equations are satisfied because on AutoCAD, our start location for bar 6 was 148 degrees, and you can see that bar 3 is at 0 degrees, meaning it's sitting flat on top of the box. Then you can see exactly 180 degrees away from that at 328 degrees, our box is at 90 degrees, which means it has moved down and rotated 90 degrees. Next, we calculated the velocity for all the bars in the motion. This was done relatively simply using a relative velocity equation. You can see here. We then came up with our I and J components, and then we had to place these into a matrix to get Excel to solve it. So what we had to do was we had to create a coefficient matrix, an answer matrix, We had to take the coefficient matrix and multiply and make it its inverse to give us the answers, as you can see here. So what we did, these are our original coefficient matrices. These are the inverse of these coefficient matrices. We took the inverse matrices, multiplied them by the answer matrices, which gave us our resulting omega 2, omega 5, omega 4, and omega 3, which are tallied here, and then tallied here from angles 0 to 359 throughout the entire motion of the bar. Here you can see we plotted the velocity. Our velocities stay pretty consistent right around 0. They don't get very fast. They peak in a couple spots here. They really peak right here. This has to be a cusp of some type. You'll see later that the accelerations also peak greatly at this exact spot too. So now we move on to calculating the accelerations in all of the bars. As with the velocity, simple relative acceleration equation. Broke it down into I and j components, then set up coefficient matrix, answer matrix. And you can see that here, the coefficient matrices along with the inverse of those multiplied by the answer matrix will give us our answers alpha 2, alpha 5, alpha 3, and alpha 4 that are recorded here from angle 0 to 359. You can see alpha 6 remains 0 the whole time because the omega for 6 is constant, as you can see here. It's a constant at 0.628. That will give the mechanism a complete cycle runtime of 10 seconds. You can see with our acceleration plotted, they also stay very consistent and peak right in the same spot along with the velocities. Next, we had to calculate the force and the linkages. I only chose to show link 2 here, but we had to do this for each separate link. So we had to create a free body diagram along with 3 equations to go with it. F equals ma, along with our moment equation. So to see here, all of our forces are shown, along with our accelerations, along with all of our equations. Now once we created the free body diagrams and the 3 equations for all the bars, we had 15 total equations and we had 15 total unknowns, which gives us this huge matrix right here. You can see equation 1, 2, 3, and so on down to 15. What we did is we created a big coefficient matrix, filled in our coefficients, took the inverse of that, put it here. We then created our answer matrix here, multiplied these 2 together to get the forces in all of our pins from angle 0 to 359 over here. If we were to take this project further, what we would be able to do is we would be able to take the forces we found in the pins and we would be able to determine the diameter of the pin needed to support the forces as well as the material of the pins. We would be able to look at the torque required for the motor to turn the mechanism, which is right around 50 Newton meters. And we would be able to look at that and we would be able to optimize that and create it more efficient. We would also look at those giant cusps that we had in our velocity and acceleration plots and try and eliminate those. And that's it. Thank you.